Hello student! Today, we're not just going to learn about capacitors. We're going to feel what happens inside them during charging and discharging. By the end of this video, you'll be able to visualize the entire process and even derive the energy stored in a capacitor. Let's jump right in. Understanding capacitors. Imagine a capacitor as a tiny supercharged battery. It has two metal plates separated by a small distance d. Keep in mind that capacitors are electrically neutral. This means that for every positive charge in the capacitor, there is an equal amount of negative charge as well. However, in our presentation here, we will only show the conventional direction of current. Let's imagine we connect a 9-volt battery to a capacitor. Here's what happens step by step. As soon as the connection is made, the battery starts hustling positive charges from one plate to the other. Each little charge, dq, needs some help from the battery to make the journey across. Initially, at the start, the capacitor's potential is 0 volt, while our battery is a solid 9 volt. The first few charges move easily, but as more charges pile up, the capacitor's plates start pushing back, saying, "Hey, we're full." The battery has to work harder to move more charges, building up potential energy in the capacitor. Second, you know that positive charges flow from the positive terminal to the negative terminal, which is the conventional direction of current. That is, the battery wants to make the charge flow clockwise.
Now, one of the plates has an excess of positive charges, making it positively charged, while the other plate has an abundance of negative charges, making it negatively charged. These excess positive charges naturally want to flow back to balance the charges. If we think of the capacitor as a tiny battery, positive charges want to flow from positive to negative terminal of the capacitor, or we can say,
it wants to make the charge flow counterclockwise. But because the potential of the battery is higher, or rather, the power to push the charges is higher, the battery will succeed in moving the charges clockwise until the voltage of the capacitor is comparable to that of the battery. An electric field forms between the plates, opposing further charge movement. This field grows stronger as more charge accumulates. Okay, now let's see the graphical representation of charge Q and time t. Graph for the process of charging. When you plot the charge Q on the capacitor against time, t, you get a curve that looks like this. Initially, the charge increases quickly, but slows down as it approaches the maximum value. Understanding expression for the energy stored in the capacitor. So, when we insert a small charge, dq, into the plate of a capacitor, we have to do some work. We know that the work done per unit charge is equal to the potential energy, which we call V. Additionally, you know that the voltage across the capacitor is related to the charge Q on the capacitor and its capacitance C by the formula that says voltage equals charge Q divided by capacitance C. When we substitute Q by C into the equation for work done, we get work done equals Q by capacitance multiplied by dQ. We know that the total work done by the battery to insert charges into the capacitor is stored as the potential energy of the capacitor. To calculate the total work done, we need to integrate. We will integrate the small amount of work done, dW, and denote the resulting energy by U while integrating from zero charge to total charge Q. This will help us to find out how much work the battery had to do to insert all Q charges to fully charge the capacitor. First, we'll take the constant one by capacitance out of the integral. You know that the integration of Q dq results in Q squared by 2. Then, substituting the upper and lower limits, we get 1 by 2 times Q squared by C. Here, we can write Q as capacitance C multiplied by voltage V. Simplifying this equation, we get 1 by 2 C V squared. Think of it like many positive charges being forcefully compressed in one place as if they are struggling to return to their neutral state. They want to come out, but the battery isn't letting them. But now, if we remove the battery, the charges will remain trapped in the capacitor, and we'll say the capacitor has become charged. The charges cannot flow because the circuit is still open. However, if we replace the battery with a bulb that has no internal EMF, the charges will flow back to their neutral state through the circuit. The capacitor will then function like a tiny battery, causing the bulb to glow for a while and then quickly discharge. This process is known as discharging of the capacitor. Now we can understand graphical representation of charge, Q, and time, T, graph for the process of discharging. When you plot the charge, Q, on the capacitor against time, T, during discharging, the curve is the opposite of charging. It starts high and decreases rapidly at first, then slows down as it approaches zero. So that's all for this video. Thank you so much for watching.